Good day to you, Trig Selected. I am absent today, so I will be making a little video to go through our notes, and then you'll just do some practice problems with the notes. We are still in Trig. We did the introduction to Trig, which was all the SOHCAHTOA stuff, but now we're going to kind of look at Trig as if it were a function, and all the rules we learned with functions before, transformations and stuff, rear their ugly heads again here for graphing sine and cosine. So without further ado, let me switch this over and let's go through these notes today. So we, on your bell work yesterday, you guys graphed a cosine curve by simply going around the circle. You guys filled out that little table I gave you, but this is a rendition of that table. This is 0 degrees, 90 degrees, 180, 270, 360. You knew that cosine was always the x-coordinate, so you fill out the x-coordinates, then you sketch a little graph. That's what we're going to do today, only we're going to mess with sine. Cosine and sine are very closely related, but since you already did cosine, I wanted to do sine today. So if you haven't already, stop looking right there and sketch what sine would look like if you went one time around the circle. We're going to have theta on our x-axis, that's our angle, and then we're going to have what the actual sine value is on the y value. I'll give you a minute, hit pause, try it out, pretend that you can't see that. Good, you're back. So as we go around the circle, sine is always my y coordinate. Sine is the y coordinate. So when I start at 0, the y coordinate is 0. And then when I go to pi over 2, the sine is the y coordinate. Y coordinate's 1. Y coordinate's 0. Y coordinate's -1. Then back to 0. So as we plot, if we go around the circle in radians, we should get a picture that looks something like this. And you'll notice a couple weird looking things here. Weird looking thing one is that I put X's here on the tops, and the bottoms are supposed to be 1, because those have a special name. We call those antinodes. Antinodes are the maximums or the minimums of our little curve looking thing here, our wave if you want to. It kind of looks like waves in a wave pool or the ocean. So these top maxes and mins are called antinodes, N-O-D-E-S. The ones in the middle, sometimes they're called equilibrium points, where it's always back to the middle. Back to equilibrium is the beginning middle. For us, we call them just nodes for math. So we have nodes in the middle. We have antinodes on the back, or on the extreme values. That's weird thing number 1. Weird thing number 2 would be these dots. What I'm doing right there is I'm saying, like, I just had you go around the circle once in a counterclockwise fashion, but is that the only way to go? The answer, no. We could have went clockwise and went in the negative direction. That would be a curve back this way. I could have went around the circle twice or 3 times. I could keep going around the circle over and over and over. So we're not just limited to one time around the circle. This thing does other things. So with your neighbor, if your neighbor is on the same spot as you, or just think about it for a second, what would the domain and range be for this graph, y equals sine theta? Remembering the domain, or all the possible inputs, what am I allowed to put into this function and get a value out? And the range are all the possible y values, all the outputs. What could it absolutely kick out? What can it kick out from our function? Okay, we're back. Domain, hopefully you could tell this thing goes to the left forever. It goes to the right forever. You can plug in any number you want. The domain is all real numbers, special R. The range, well, the highest it ever gets is 1. Never gets above 1. The lowest it ever gets is -1, and it's all values in between that. So for the range, we would say all values between -1 and 1. So here, for the range, values between -1 and 1, with a bracket, because we can include those values. And then for the domain, we said all real numbers, so we'll put that special R. You could do from -infinity to infinity if you wanted to. They mean the same thing. But this is like our general introduction. This is our parent function for sine. From here on out, we're going to start doing some different stuff with it. So that leads me to the next thing. We'll have a little definition here. In general, all these trig functions deal with going around a circle, and a circle never ends. So we call these periodic functions. They repeat themselves. If you go around the circle, you're going to notice patterns. They're going to start to do the same things over and over and over, because we're going around and around the same exact circle. So hopefully that makes sense for us. But we get a little vocab word there, a periodic function. Okay? Let's try another example. I would like you to sketch, sorry, there's a bug, killed it. Sketch a graph of 5 times the sine of x. So notice I'm not using theta anymore. We can use any variable we want, but we're still putting angles in here. And in fact, I want you to put the easy angles, those cardinal directions, 0, pi over 2, pi, 3 pi over 2, and 2 pi, and then take the sine of them. So we're going to do this. Before we do this, hold, those of you that are running and doing this, what transformation are we dealing with? Right? There was a reason in yesterday's boot camp problems that we did what we did. What transformation was it when we multiply the outside of our function by a number? Answer, a vertical stretch. This graph is gonna look almost identical to the one you've already done, except we're stretching, we're pulling all these y values away from the x-axis. It's stretching apart, and it's actually, instead of only making it ever up to 1 and down to -1, this one is gonna make it up to 5 and down to -5. So if you sketch a graph, if you go through and plug these values in, like let's plug in 0. Okay, the sine of 0 is 0. 0 times 5, 0. No big deal. But what about pi over 2, that first point? Pi over 2, the sine of pi over 2, my y-coordinate is 1. 1 times 5 is 5. So instead of only going up to 1, we're going up to 5. Your other function, the one you guys just did, would only have made it up to 1. So here, let's do it in pencil for future generations. The one you guys just did, 1 is right there, -1 is right there, would have looked like this. That's the one you just did, but now I'm pulling it apart. I'm stretching this thing out, and we get this new definition, right? Anytime we're learning something new, it comes with its own vernacular, its own vocabulary. We get something called the amplitude. When we have a vertical stretch or a vertical shrink, we're going to get something called amplitude. And actually, there's amplitude on all of these. There doesn't have to be a vertical stretch or shrink. Even the original one, the one in pencil up here, has an amplitude. I gave you 2 definitions for amplitude because it depends on what information you're given as to what definition you should be using. Oh, the little mute button is hit down here, and it's really stressing me out. It's still hit. I don't know. Let's keep going. The first definition is half the distance between the max and the min. Okay, so the maximum is 5. The minimum is -5. If I find the distance between those, that's 10. Half of that would be 5. That should sound familiar to you. Half the distance between 2 numbers. That was on yesterday's boot camp. How about the distance from a node to an antinode? Vertically, when we're talking amplitude, we're talking up and down. So if my nodes are at 0, and my amplitude is, or my antinodes are at 5, that distance from here up to here, that is also an amplitude, 5. So just depending on what information I give you in the problem, that's going to depend, that's going to tell you how to find the amplitude, which one to do it for. Okay, so we have periodic, we have amplitude, we have nodes, we have antinodes. I tried to underline all vocabulary in yellow to help us when we play our vocabulary game, but let's keep moving ahead. Next one. Take a look at this example. What transformation are we dealing with here? Okay, well, I see amplitude of 2. It's going to be stretched out 2. But also we have a +4 tacked on the end. The outside of my function is changing my y values. It's a vertical shift. We're taking all the values we would get for this thing and then moving them all up 4. Okay, so we have a vertical stretch. We have a vertical translation. No big deal. We're still going to use those key values. If you haven't figured this out yet, you should probably put this on your notes when you're graphing these. This is a very handy thing to do because these are all those quarter points, those really easy, not quarter points, all these cardinal directions, where sine, in this case, is going to be the y-coordinate. So I'm going to plug in for 0. Sine of 0 is an angle of 0. That's right here. I want the sine. Well, the sine is the y-coordinate. The y-coordinate is 0. 2 times 0 is 0. 0 plus 4 is 4. So my first point is actually going to be I plugged in a 0 right here, and it kicked out a 4. How about if we do this one? Okay, that's pi over 2. I'm plugging in pi over 2. Sine of pi over 2 is 1. 1 times 2 is 2. 2 plus 4 is 6. Okay, so I plugged in a pi over 2. It kicked out a 6. We go around the circle, and we're going to get what we're going to get. I actually made it into a table this time. All right, there's my key values, cardinal directions going around the circle, and I plug them in. Notice we're going to start getting like patterns here. I don't have to graph it with the table. Okay, hopefully you guys can start to pick up on this. I can just plot the first point, and that's what I'm going to do. I'm going to plug in a 0, sine of 0, 0, 2 times 0, 0, 0 plus 4, 4, 1, 2, 3, 4. And then I know when I move over to my next point, it's going to change by whatever the amplitude was. Well, the amplitude was what I was stretching it by, a 2. So I know when I move over to my next point, which is pi over 2, it's going to have to increase by 2. 1, 2. Nice. On the next one, when I move over to pi, it goes back to where it started. It's going to go down to a node. When I go to the next one, 3 pi over 2, it goes down again. So I'm going to go down 2 from where that was. And the next one, 2 pi, it goes right back to where it started. And I get this curve without necessarily plugging all the values in. You can plug the values in, and you should to get a lot of good practice, but you don't have to. Okay? There's the same thing. We're on to one last note. The question is, on that very first one, for a normal sine graph, where were the nodes at? So I'm looking for it. Here's our normal sine graph. Where were all the nodes, the middle ones? The answer, 0. They're all sitting here right at 0. For the one we just did, for y equals 2 sine x plus 4, where were all the nodes? Okay, should be in your notes. I'll bring it back. Okay, all the nodes, node, those are all at 4. So we can make a generalization with this. And we can say, whatever the vertical shift is, that's the middle of my graph. That's where that equilibrium points are. That's where the nodes are for this thing. So that kind of helps us sketch these things without necessarily plugging in every single point. Last one. Oh, here we go. Without graphing, I want you to figure out what the domain and the range are for this function. Put it all together. Let's take that leap. Okay? Let's start with the domain, because that's the easiest one. The domain are what I'm allowed to plug into this function. Anything you want. Positives, negatives, fractions, decimals. You can plug in anything you want and take the sign of it. Times by 4, subtract 3. Good. But now the range gets a little bit different. We want to know what's the lowest value it ever gets to and the highest value it ever gets to. Here, let's already start here. We know it's going to look like that. I'm really asking you for the max and min. But based on what we just talked about, the nodes, the middle of my graph will always be at -3. And then I'm always going to change it by 4. So from -3, I'm going to go up 4. Well, that would be 1. That's the maximum. And from -3, I'm going to go down 4. Oh, that would be -7. That's the smallest it'll ever be. So this graph is just going to bounce back and forth between -7 and 1, -7 and 1, -7 and 1 forever. So let's see, -7 and 1. There is -3. It's going to go up to 1, down to -7, up to 1, down to up to 1, down to -7, up to 1. You get the idea. Domain, range. Here's all the same things I just said, written in this form. So I know I wasn't here to answer a lot of the questions, so just do the best you can with the worksheet the sub's going to give you. I'll come back tomorrow. We'll start filling in the gaps, and we can start taking tricks and hints. And obviously, it doesn't stay this easy. We're going to have to build on this. But first, let's get good at this one. Moving on.